Welcome back, everyone, and we're going to do another video, and we're going to continue off where we left off before. In the previous video, we actually retargeted our animation frame by frame and saved out a brand new animation object file. So what we did was we then converted all this animation data and export it right back out as a GLTF JSON file and binary file that we were actually able to download from the page. And then we actually able to load that up in a different page and run the animation on our Vegeta character. So in this video, we're going to continue that and take it one step further. We're going to take that retargeted animation file and then we're going to build it into, I think might be considered called a data texture. So it's really just a texture file, but it's going to store data in there. And excuse me. And what are we doing? Why do we need to do that? The one thing we can do with it is that we can start moving all our animations onto the GPU. What else? So we have everything. So we don't need our animator. We need our pose. We don't need to recalculate. Technically, you end up caching all the world space transformation offsets into a texture file. And that means you don't have to recalculate the animation ever again. We actually have the final animation is one big texture file. And why a texture file? Well, a texture file is we can store lots of information. We can store boatloads of data into a texture file. Because you can't store stuff in a uniform. There's a limit to uniforms. So there's a limit. And so this, like I said, you can store a lot more. You can store quite a bit of information in there. And the real big reason why we want to store everything as a texture is that we have random access to the texture. Since all our information is really just fluid information, textures pretty much can't store floats. You can configure a texture to say this every pixel represents a vector 3 or a vector 4, and they're all represented as floats. So if we want to make a bunch of data of just vector 3s, we just say, well, we want a texture that's configured that every pixel is RGB. If you want to store 4, like a vector 4, every pixel has to be configured as an RGBA with an alpha. And then let's say if we want to store more than one bit of information per set, we can say, well, we need to store this bit of like a matrix. A matrix is a 4x4 matrix is 4 floats, columns and 4 floats. So it's like 12 floats in total. So ideally, you can then say, well, I need to store a single matrix in 4 floats, in 4 pixels. So if you set a pixel for 4 floats, then a single matrix will take 4 pixels worth of information. So that's what we're going to do. So let's just kind of go right to it because my throat's starting to fall apart. So here's I'm going to really just drive through this a little bit. So we're going to take all our animation data and we're going to store it as basically an image. But we're not really storing it. We're just storing it as a big giant blob of byte arrays. Just a big giant byte array. In the previous video, I went a big spiel about how some people have difficulty dealing with things where it's data oriented as opposed to object oriented. So we're going to kind of go through that again a little bit, where it's just how we're going to store the data and how the data is represented. So we're going to store the data basically like this. Every X represents a single pixel. Every pixel is considered RGBA. So because we're going to store all the data as dual quaternions, not matrices. Our armature system that we've developed uses dual quaternions, not matrices, to actually represent the data for our armature. So this way we actually have half the data that we need to push to the GPU. So this way we actually store data and store it. The only thing we do have to do is that we have extra functionality in our shader that does the calculations for dual quaternions, because shader code already has things built in to deal with matrices. So that's like the only caveat by doing dual quaternions, is like you kind of have to write extra functions in GLSL, which is like a C language, to actually represent all the mathematics to handle a dual quaternion or a quaternion in general, because the language itself doesn't handle quaternions either. So this is what our data is going to basically look like. It's going to be just a bunch of pixels. and our texture is going to be 6 pixels by 3 pixels. So if you look at an image, it's like just a big blob of information, and normally in an image, you know what's the dimension, it's width and height of an image. So that's going to be our data texture. How is that data represented? So our data, so to think about it, like this is how it's really represented. This is what it really looks like. So like I said, we need 2 pixels for every dual quaternion, because every pixel represents 4 floats, and dual quaternions need 8 floats. So that means every 2 pixels represents 1 dual quaternion. And we know how many frames we need. So if our animation has 3 frames, that means every 6 pixels represents an entire animation for a single bone. So if we know that every single bone has about 3 frames worth of information, this is a single bone of information for an entire animation. So this is bone 0, this is bone 1, and this is bone 2. So it's 3 frames, dual quaternions, 2 pixels each. And this flat blob actually looks like this. That's how we're going to interpret it. That's ideally how we're going to convert it into. And when we need to pass, once we pass this data into the shader, we need to access it. And that's one of the cool things about textures. We have random access, and there's a special function in there that we can call that gives us the exact pixel. Instead of giving us like a general pixel, like using the UV, we can say X and Y. We want pixel 0. So let's say we have a vertex that uses bone 0, right? We have a vertex that uses bone 0, and we're currently in frame 0 of the animation. So I know, every bone index is a row, right? So that's bone 0, bone 1, bone 2. So X equals bone index times, actually no, that's it. It's bone index. Sorry, X is just bone index. Because I'm thinking about, this is a 2D matrix at this point. The data is stored as a 2D matrix. It's not a flat array anymore. I was thinking of flat arrays. So that's all it is. So if our vertex says, okay, it's attached to bone 0, the X position. Oh, I'm sorry, not the X. I am so sorry. I should have wrote this. The Y position, because it's Y. If this is X, and Y is going down. So the Y position, the Y position of our texture is the bone index. The X position, now we're going across. Now that's the frame. That's the frame. So if we're in frame 0, so you have frame index times 2. That's it. That's all X is. So if frame is 0 times 2, that means X is 0. If bone is of Y, so we have an X of 0 and of Y of 0, and that means it's this pixel. That's the pixel we're going to access. Well, we know it's a dual quaternion, so our function says, okay, I know that's the pixel. I'm going to grab the next pixel over on the X coordinate. And that will, so now I know, so I have, like I said, the function will automatically say, well, I'm going to grab the next one over, and now that 2 pixels represents our dual quaternion for our frame. So if I want to access, let's say, this bit of information, that is bone 1. So now our bone is bone 1, and we're on frame 1. So if Y is just our bone index, it's 1, so that's 1. So we have a Y of 1. And X is our frame index times 2. Frame index is going to be 1. That's that's frame 1. So 1 times 2 equals 2. So we have an X of 2. So if that is pixel 0 and that's pixel 1, this here, the third one, is pixel 2. And that's where we're going to start. We're going to say pixel 2. That's where we want to go. And that's how we're going to access the data in our shader. It just some simple mathematics to translate bone index and frame index into the 2D matrix of a dual quaternion. So it's really just a 2D dual quaternion matrix. And that's it. And that's how the data is going to be laid out. So, like I said in the previous video, I'm going to write big, huge steps that explains everything, but I pretty much already told you everything that we're going to do. So, I'm sorry, my phone is falling apart. So first thing to do is we're going to load up our shader. So we're going to look at our shader a little later. And we're going to build our material for our shader because we need a material. So the material is going to hold our shader, and it's going to hold a reference to the texture that we're going to generate. Now we're going to load in the GLTF and the binary file that we created, that we exported, that we targeted. We're going to reuse it from the last video. We're going to load the animation from it, and we're going to load in the skin for the mesh. Now we're going to run a function that says convert the animation into a texture, and then we're going to run another function that says create a data texture on the GPU and dump the information into it. Just dump it. Just like how we dump an image into a texture, we're just going to dump it. It's just like any other buffer. We do like a float array for our regular buffers. Here's a float array. Just dump it into the GPU, into our buffer space. Simple, done that. And then, since we have our texture that got generated, we add it to the uniform of our material. Like I said, our material has our custom shader that's going to do all our skin animations, and that's it. And I say we have the animator, but it's the reason why I have the animator is just so we can go through the animation and calculate its world position. The animator is not actually used to animate. It's only used to compute the animation once, and the animator goes in the garbage. We don't need the animator after we're done computing it. Like I said, so if we go into our onDraw event, there's nothing happening in our draw event. Our draw event is we run the ECS system, and that's it. There's no extra functionality that we're doing. There's nothing else we're doing out of the ordinary. It's just processing the regular data that exists in the system, and then drawing it onto the screen. Like before in the previous videos, we had the animator that was running and it was doing all these other fun stuff. All right, so let's look at animating to our texture. So it's actually not that, it's really small. It's really not much to it. So what we're going to do is that we're going to create a float array. Like remember, we're going to store this big blob, right here. And we're going to know we know it's our pixel width and our pixel height times 4. Because it's 4 floats for every pixel. So how many pixels are there? So we know our pixel height is our bone length. Like I said, it's how many bones we have. And our pixel width is really just how many frames we have times 2, because we need to store dual quaternions. Every frame is 2 quaternions, and every dual quaternion requires 2 pixels. So frame times 2 is our pixel width. And then our row of pixels is our pixel width times 4, because we need to convert it into floats, because we're creating floats, because this is a flat array. And that's it. There's really not much else to it. So once we have we created our float 32 buffer, array buffer, we can then just take our animator, say, okay, and like I said, we're not going to animate. We're going to just step through every frame of the animation. We're doing no interpolation whatsoever. So we just say frame 1, here's the animator, save it to this pose. And pose and animator is created here in this function. Like I said, once this function is done running, animator and pose goes in the garbage. Hopefully goes through the garbage collector, and we don't need to deal with it anymore. So we animate it. So we animate 1 frame. We update its world position. We calculate its starting position in the array. Every frame starts frame. Then we just loop through all our bones. And let's see, we have to grab our bone component. That's the only problem. We have to go back to our bone component to get the actual bind pose of the armature. We grab our animated pose. We figure out the starting index for to store it into our flat 32 array. So the first thing we're going to do, we're going to take our pose world space rotation and our pose or animated world position and rotation, and we're going to set it into our dual quaternion. So this is what we're just setting. We're creating a dual quaternion from our world space animated pose. Then we multiply it by our bones bind pose, and the bind pose is also a dual quaternion. It's in world space, but it's inverted. I don't know if I want to really go through the hassle of explaining that inverted pose. Videos ago when I started doing armatures, I explained that more fully. So if you don't understand, please check out the video. If you really don't understand why I have the bind pose inverted, just comment and I'll probably try to quickly explain it to you. But that's all we need to do. We need to take our current position, convert it into a dual quaternion, and then multiply it by our bind pose, which is an inverted world space dual quaternion, which creates us a dual quaternion offset. So what is the difference between our bind pose and our current pose? That's all we're doing. We just want the difference. What's the difference between it? What's the change? Once we have that change, we just store it into our buffer. So I know the starting point for the frame, like the X and Y coordinates, like essentially, but in the flat array version of it. That's why I made a mistake in the previous when I was looking in the other file, because I was thinking this way as a flat array coordinate system is different. So we have a dual quaternion, we just dump it in, and then we kind of return like a tuple. JavaScript doesn't have tuples, but it's essentially just like 3 values. We're just returning 3 values, and I return it back as an array. So the first part of the array is the width, the height, and then the actual flat array. Again, so that's here. So now we know the information of our animation, animation information that's been converted. So all our animations have been converted into world space offset dual quaternion values. Nice big flat array of it, and it's designed as a matrix. So every bone has a row, and every column is a frame. So that basically the entire animation, like the final product, the final values of every frame for every bone that we normally would calculate and throw to the GPU one frame at a time, we calculate the entire thing and save it into one giant blob of byte data. Right now it's a float array, but its array buffer itself is just a byte array. And then we need to create our animation texture, which that's not the file, it's this file. So we create a texture, we bind it, and then we set these specific settings. So this way we could turn off filtering. So this way, normally when you do like an UV thing, you say a certain pixel, and if it's set to, I think, linear, I forget what the other setting is, but there's a different setting that it uses. Let's say if it, like the pixel is like in the middle, you have a black or one pixel is black and one pixel is white, and you pick that pixel, like that's kind of like in between. Instead of giving you black or white, it'll give you gray. By turning off filtering, you kind of don't do that. You either get black or white. You don't get like an interpolated version of it. So that's what we're doing. We're making sure we don't interpolate any of the pixel information, because we're not dealing with image data. We're dealing with actual flat animation data, and we don't want anything to change. We want don't interpolate the data. We want the real data. We don't. So that's what we're doing. Turning off filtering. And then that's it. Then we kind of set. Sorry, my throat's really hurting. So then we just kind of set what the texture is supposed to be configured like. So every pixel is an RGBA 32 float, because that's the data we need. What kind of format it is? It's just an RGBA. And what's our actual data that we're going to pass in? We're passing in a float 32 array. And then that's the data we're passing in. And we unbind it. Like I said, there's really no difference from making a texture from an image as opposed to making a texture from data. The only thing is it's just slightly different bits of configuration that needs to change, because we're not treating it as an image, we're treating it as data, as a data texture. And that's all we need to do to create a data texture. So once you have that big flat 32 array, just plop it in there and you're golden. And the last piece of the puzzle is the shader. And the only thing we need to do in the shader is everything in the Vertex shader. We don't have to deal with anything in the fragment shader. Normally we usually get the texture in the fragment shader, but this time we're actually going to use the texture in the Vertex shader. Let's see. So, this is like a regular skinning stuff. So we have our position, our normal, our UVs. We have our bone index and our bone weight. So this is traditional, what we've done a long time ago in the past when we started doing armature animations. We save everything through a UBO because uniforms itself has limited, so we can actually store everything in here. And if we need to animate more than one thing, let's say if we have like a body that has and sometimes some models are broken down into pieces, but they all share the exact same armature. So if we, let's say, load the armature once, but then render multiple meshes, it kind of saves us time from actually loading the armature for each shader and for each thing they're rendering. So if we dump everything into UBO, we do it once, and then we can render as many times that armature as we need to. Just once. It's efficient, and I think UBOs can store more data than uniforms itself can. So that's why we have the uniform UBOs here. And then we kind of pass in our reference to our shader, to our texture, I should say. And now here's the thing. This example does not deal with time at all. I'm not interpolating the animation. I'm actually just displaying every frame at the right time. I'm not interpolating. This is a bare bones example, so there's no interpolation of the animation. So the animation will look kind of good, but if you look closely, you'll see that it's slightly choppy. You have to really focus on it to see the choppiness, because we're not interpolating between frames. If we're interpolating between frames based on the actual frame rate, the animation would be regular, how it normally would look smooth. So just keep in mind, this is a bare bones because I'm not dealing with time or anything else. This is purely just getting the data into the GPU and then be able to render every frame of the animation. And the animation from Mixamo is already baked at the frame level. So Mixamo gives us 32 frames, and it gives us a time for each frame. But like I said, we're not worrying about time anymore. So if I know the animation is 32 frames and it was baked at 30 frames a second, then I know how to basically calculate. So this way I know how many frames it is and the actual total length of the animation. That's how long the animation is. That's all information we need for now. Close this for now. We don't need this. We don't need this. We don't need that for now. And I call it U because they can be uniforms in the future, but for right now, I'm making them constant because I don't want to pass in more uniform information. Like I said, I want this to be a simple example built for just this one lesson. So we have the global time. So we know what the global time is in our shaders, because in our render loop we calculate the time that started. So from the time we start rendering till now, we keep track of the time. So it's 1 second, 2 seconds, 15 seconds. If we sit there with the page open, then maybe it's been animating for like hours. So we know the time since our system started. So we do a modulus. So the modulus basically truncates our global time between the values of 0 and this value. So if global time, let's say, is 10 seconds, but our animation is only 1 second, global time modulus is going to give us a value between 0 and 1, which is basically probably 1. But let's say if it's like 10.5, it's going to give us back a value of 0.5 because it exists between 0 and whatever animation time is. So like I said, that's why I'm storing the total time, because I'm going to truncate the global time between the values of 0 and the total animation time. So now I know the actual time of the animation. then I normalize the time. So that time divided by the overall time. So let's say if it's 0.5 seconds and the animation is 0.1.0 seconds, what's the normalized value of that? Okay, so I got normalized. So I have to get a value between 0 and 1. So I know how many frames do I have? I have 32 frames. So take that normalized time and multiply it by frames. Right? So this way it gives us like a frame. It'll tell us if we it might give us like say 10.2. So it's basically the 10th frame, but it's 0.2 after that. So it's like so we need to interpolate between 10 and 11 by kind of like a 0.2 value. But we're not doing interpolations. I'm not, like I said, I'm ignoring that. But that's how you would kind of go further. In tutorials in the past, I've done animations. Like you just look at the animator and just copy that code into GLCL or GLSL if you want to do interpolation. But like I said, I'm ignoring interpolation. So if I'm ignoring interpolation, I'm going to floor it. So this way I get the starting frame. So like I said, frame is 10. Moving on to frame 11, I don't care about frame 11. I'm not going to interpolate to frame 11, so I'm just going to say frame 10. At this current time, the starting frame is 10, and I'm going to stick to it. That's frame 10. So now I know what the frame value is, and we need to convert it into an integer, multiplied by 2. Now I know the x position for our pixel. Remember it says frame index times 2, and that's our frame index times 2. Done. Need some water. And we know what our y is because our y is our bone index. But our bone index can be multiple bones. So we know which frame we want, but we're going to grab multiple bones of that frame. So if I go to dual contouring bone texture, I go here, and this is what our normal armature thing kind of looks like. So we grab all the index of the bones that we have access to. We have four possible bones that we can do. I'm sorry. Then we're going to normalize our weight. If the data weight from your mesh is normalized, you don't need this step. But if it is not normalized, then you need this step because else it will crap out. You get really bad stuff. So ideally for optimization, if you want to make the maximum amount of optimization, you make sure that the weight vector for every vertex is normalized, so you don't have to do it in GSL. So if the data comes in already normalized, you can actually take this step away. Next, we're going to grab every dual contouring pixel that we need. So every dual contouring is 2 pixels. So we're going to grab that bone, bone B, bone C, bone D. We're going to get the dual contouring of that frame. So like I said, that's the X position and that's the Y position. The Y position is the height. It's the bone index. So that's the bone index. So we're actually going to grab it's 2 pixels each. So we're going to actually grab 8 pixels of information and convert them to dual contouring and then multiply them by our weight. And this is the same thing as we did before, where we actually got our dual contouring from our UBO. We would normally get it from here, our UBO armature bones, but instead of getting it from here, we're actually getting it from our texture. So that's the only big difference, is where we're getting the dual contouring from. Once we have the dual contouring, we multiply each bone by its weight, and we add it together to make a total dual contouring value. So that's the total sum. Like this, that's all. Like this vertices is being manipulated by 4 bones, but each bone has a different amount of control over it. So one bone might have 0.5. That means it has a half the control over it, and all the other bones have like 0.1, 0.2, whatever. But it equals up to 1 value. It equals up to 1. The total weight is equal to 1 when you add them all together, and that represents the total. There's a word for it. I can't remember it now. The total. I can't think of it. It's the total influence of bones on that vertex, like how much to rotate it and how much to change its position. That's the influence. So that's our total. This dual contouring is the total influence of for that's applied to it. And now, anytime you do any type of a lerping, or this is kind of like lerping in addition, you need to normalize. I learned this a couple months ago that there's certain issues, and once I normalized it, it fixed the problem. So dual quaternions need to be normalized. It's just like quaternions. If you do anything with quaternions, you need to normalize them afterwards. Like, not if you multiply them, but if you do it lerping or like just add regular addition and things like I said, we're doing regular addition. It needs to be normalized. So dual quaternions get normalized by the length of the quaternion. So even the dual quaternion part that deals with position does not get added to the length. It's just the length of the quaternion aspect that does the normalization. A nice optimization might be to do this, because I do the same thing here, because at this point I'm going to do 4 divisions. No, I'm going to do 8 divisions. So it'd be easier just to do 1 division and then do 4 multiplications. So I'm probably going to save it, and if the code runs beautifully, good. If the code breaks, I'm going to switch it back. But this should work if you want to optimize it. Like when I wrote this, I totally forgot to optimize it. Oh, and it's 0.0 because we're dealing with floats. And then we just give it our dual quaternion and our vertex, and then just multiply our vertex by that dual quaternion. Now, how do we create the dual quaternion to begin with from pixels? Super. We use a function called texel fetch. Texel fetch allows us to get the exact pixel that we want, and by having it configured with like no filtering, it makes it super easy to pick the exact pixel that we need. So that is very important. So we need there's another function for getting pixels, but that one kind of gives you the general location. That's kind of like a UV, and this one is like more XY. So this is, like I said, this is the exact pixel that we want. So we're passing in our XY, and like I said, the next pixel over is the second part of the dual quaternion. And I take the 2 pixels, which are two vector vors, and just put them together into a matrix, a 2x4 matrix. And a 2x4 matrix is what represents our dual quaternion. So when we come back to here, we can do all our dual quaternion mathematics by using a 2x4 matrix. The end. And the way we multiply is this. We dual quaternion is a 2x4 matrix. The first one is the rotation. The second one is called dual, but it's our translation. It's our position. And this is how we rotate a vector from a quaternion. And this is how which kind of sucks, but this is how we turn that dual value into a position. It converts it right back into a position, and that position gets that translation gets added to the vertex position that we rotate. So we have this rotated position plus our translation, and that's our final thing. And that's it, and that's our shader as a whole. And then once we have our position, and then we do everything else that we normally do. So if I go to our page, I go to here, I click to here, and let me refresh. Everything works fine. The optimization that I threw in there works. I was right. And there you go. And if you pay attention to the animation, to me it looks a little choppy. There's some kind of smoothness that's missing from it. It's not perfectly smooth. And like I said, because I'm not interpolating from frame to frame, I'm just running frame to frame. Frame A, frame B, frame C. There's no frame 1.5 or frame 1 1/3, whatever. That's it. That's all we're doing. But there you go. That's how we like I said, you guys can take a step further and start doing interpolation things. But I really wanted a bare bones example of how to convert like an existing animation data and then put it into a texture, and then just get it simply running on the GPU. like I said, this you can take this a lot further ahead. You can do blending and everything else. You like load up 2 textures and then blend between 2 different animations. You could, like I said, and there's probably things we're going to explore in the future, just not yet. But like I said, this is really cool. This is fun, and it's super optimized at this point. There's someone I know who's writing a book on 3D animations on Twitter. Maybe I'll put a link to him in the description. He might be worth checking out. His book I think is going to come out in January, and he recently just posted that he did the texture thing. So, and I said, hey, I did it. Why did you? Why are you saving it as a? I remember Twitter was like, well, why did you save it as an image file? Can't you just save it as a flat array? And I sent him a link to a tutorial for WebGL that does it, but using matrices, because he does matrices. I do dual contortions, and he's like, oh, I didn't even know that you can do just flat arrays. So, I hopefully in the book, I won't be naming the book, but hopefully in the book when he's done writing it won't be making PNGs anymore. It'll just be flat array, just these blob files that So it's a book I might end up purchasing because he does show samples and things online. And he's helped me a couple of times with some issues I've had. He's the one who showed me like the contortion issue where if the animation the rotation is exact but it's inverted, like the axis is inverted. So all you have to do is negate it, and the animations like the issue I had with Vegeta's butt falling apart during certain animations. He helped me fix that. Like I didn't realize that contortions can even though they're inverted, they actually rotate the same way, but when you apply them to vertices, they apply wrong. They don't work well. You have to put them in the right direction based on the starting something. I forget, but overall I know how to do it. I've mentioned a couple of times through a series of it. But I guess I'm promoting him because his book's coming out soon. So he's not a personal friend. He's just someone who's helped me out, so I just kind of want to, like push forward. So someone helps me, I want to help them. So but I'm definitely want to check out his book because everything I've been doing for the past year, he kind of just wrote a book about it. So I would love to see how he does it as opposed to how I do it. So I'm sure I can learn a couple of new tricks that maybe I'll make some videos about and stuff. So. Let's see, this is already almost 40 minutes long. So yes, please like and subscribe. I have a Patreon as a tip jar, so just pass me $1 if you want. Follow me on Twitter if you want to see the progress of all the videos, so you get to see this stuff weeks in advance, see the code sometimes, see the follies and the mistakes and the errors, because it's fun to see the errors and see my frustration when things don't work. Then see my reaction when things do work. This is this textures, and who knows? So that's it. So this is how we animate everything on a GPU. Do this entire skinning in a GPU. So it's fun. It's really cool to really just in the last couple of videos we did a lot. We're learning a lot about animation, like actually how to do animation at the very low level. It's very interesting to me to be able to do it and to do it in a very data-oriented way, and just how to deal with GPUs and really, it's fun. I'm excited. I wish I could do this stuff like all day long, but I have a day job. And if life is if the code gods are nice, I might get a new job where I might be doing this full time, but that all depends on the digital gods giving me the opportunity that I want. So I have a couple things in the works, but nothing 100%. So I probably wouldn't say nothing even at 25%. It's like I said, I need a miracle, but it doesn't matter. I'm going to do this. I'm going to do this one way or another. Either I do this as a day job, or I'm going to do this as a personal night job, because it's fun. I love it, and I kind of hope to build a game from scratch with all this code that I've been writing. At the very least, maybe someone else will write of game with all the code I have put together. So yeah, that'd be great. I would love to see a game, and I will. And if you make a game, using a good amount of my tutorials to teach you how to get there, I want you to make a 3D mesh of of a character that looks like me, and I just want to be an NPC that walks around, that's just excited about stuff. And I'll love it. That it would be really cool. Make me an NPC, and every time you come talk to me, I start talking gibberish about animation. You know, be like you click on me as you talk to me like I'm in a village somewhere in a pub, and you have your character walk up to me and say, "Talk to this guy." It's like, "Oh, cool! You look at your animation skin. You're awesome," or I don't know, something stupid. I don't know. Just make me goofy. I don't know. I'm a goofy person, so I would love to be in a video game as an NPC that just talks gibberish to people, like a drunken programmer. Yeah, make me a drunken programmer. If you make a game and you want to have a fun NPC, put me in there. I'll gladly, freely do any voice acting for it, and just make me the drunken programmer. It would just sit there and just talk about code, and it'll be more funnier in an RPG fantasy setting, because it makes no sense why this guy's talking about code when there's dragons and skeletons walking around in the world. So if you want to have fun, you can throw me in there. Like I said, I'll gladly do voice acting, because it'd be hilarious to be a character in a video game. Just a stupid character that makes no sense why he's there to begin with. Just there. If anything, I might do that myself at someday. So we'll see. I'll be in my own video game, and I'll be the drunk programmer talking gibberish. So I think I jived on too much about this. Yeah. Hope you enjoyed it. Hope you learned a lot. I think moving forward, I'm going to start finishing up some models that I've been trying to fix. And the next thing, I'm going to start prototyping, start building character controllers, where we're going to have idle position and then walk and run, and see if we can blend and start making Vegeta walk around. Because it's about time Vegeta starts walking around. Or like I have another mesh that I might be using too for it. So yeah, start making characters walk around this dark world of ours. Hopefully make them walk, run, jump. I would love to make them fly. And then once we have the character actually interacting with this world, then maybe I'm going to start going into building terrains, so this we can have a character walk around in terrains. You know, once we have a character, once we have life, then we can start expanding and building the world, because this world is too empty. You know, we need a world, but instead of like, I know a lot of way the games are made, you build a world, then you build your characters. I've done the exact opposite. I'm building my characters first, and then I'm going to build the world around them. So, because this is the hardest part. All this animation stuff is actually harder. There's just less information, less info on it. So I think that's why the guy on Twitter is writing a book, because there's really not a lot of information of how to build the system. So I kind of find it funny. I spent a year writing YouTube video tutorials about this, and he's been spending a year writing a book about the exact same subject. So it's kind of funny. You know, birds of a feather, right? Flock together. So I guess I'll see you guys in the next video, and hopefully if you watch me on Twitter, eventually you'll start seeing prototypes showing up soon of character controllers. And now, when I do prototypes, I usually put links up so you can actually see it in action running in real life, and sometimes how they fall apart. So, okay, I'm making this too long. My throat really hurts. So I'll see you guys in the next video, and yeah, hope you enjoyed it. This is fun. Bye-bye.